All right, so this is something called, this is highlighting two things. There's words in the written thing here. So they're showing us an ester plus water, and the problem says, which are the expected products of this acid catalyzed reaction? So this reaction actually is acid catalyzed, but for some reason, they wanted to test our reading comprehension instead of just writing H plus catalyst above the arrow. Don't know why. So that was there. All right. So this is an acid catalyzed process, right? So if you see an ester in water and acid, you should think, well, this is going to become a carboxylic acid, right? And you're going to make an alcohol, right? So hopefully you recognize that, that's hydrolysis, that with water around, you're going to cleave this ester bond, right? So it's also kind of challenging when they draw things like this instead of drawing it like that. I always think it's hard to recognize this kind of, we don't really do it this way, but in standardized tests, it's easier to put things in there this way to shorten it up. So what happens? So what's going on here? What's the weird thing is this 18. So what they're saying is this is oxygen 18. This is oxygen with a different number of neutrons, right? So they use this for NMR. So this is about an NMR active type thing to understand the mechanism. So one way is we use NMR to help understand how a mechanism happens. So what this is kind of asking you is, do you know this mechanism? Do you understand this mechanism? And if you do, you'll see that this oxygen, right, this bond is the bond that gets cleaved, right? And so that oxygen right there ends up on the final alcohol because this oxygen comes from water, right, just according to the mechanism. Right? So it's a way to track that. So that's what they're looking for here. So in this, that would be the right answer. So they're looking for this isotopically labeled oxygen, which is just really asking, do you know the mechanism? Right? Where does that oxygen that started on the ester end up at? The product ends up on the alcohol. All right, so for this one, it's one of the first reactions we learned. It's an alkene reacting with Br2, so it's an addition reaction. We're adding something to this alkene. The alkene is the nucleophile. The BR is the electrophile because it can be polarizable, right? Because bromine's so large, it can be polarizable. So what happens? The pi bond reacts, breaks the bromine-bromine bond, and then actually the bromine comes back down. So it's 3 arrows, and we make this special intermediate called the bromonium ion, which is the intermediate that I always forgot when I took organic chemistry. Now I remember it. But the interesting part about the bromonium ion is it adds on one side. Right? So there's a couple ways we can look at this. There's your bromine. This is the way I like to look at it. Have the bromine in the plane and have the other things coming out or away from me. So if you look at this initially, it always helps to draw in the H's on these alkenes if they're not there. You have 2 H's, right? So the H's are both on the same side, right? And so are the carboxylic acids. Just by looking at this alkene originally, right? 1, 2. Right? This is a cis, Z same side, or Z alkene. So the H's are on the same side, the carboxylic acids are on the same side. And the other thing, of course, that we made here was a bromine. Now, you do need to understand the mechanism a little bit here, that when bromine adds, you're going to add 2 bromines, and you always get a trans addition. So maybe you don't remember the full mechanism, but right, this is an SN2, and we always go for the more substituted carbon, but in this case, both carbon 1 and 2 are equal substitution, so it doesn't matter. This molecule is symmetrical, so carbon 1 and carbon 2 are really the same. But what this gives us is these 2 bromines that are trans to each other. And you'll notice that the H's that were cis to each other are still cis to each other. Right? That doesn't change when the bromines add. And the carboxylic acids are also still cis to each other. That didn't change when the bromines added. Right? So what you really need to make sure you see are a couple things. When you saw this, whether you remember the mechanism or not, you know it's going to add 2 bromines, and you should be triggering in your head trans. The bromines are going to be trans to each other. The other thing you should think about is if this alkene The way this alkene is constructed to start matters. That doesn't change because we do not go through any carbocations. With bromonium ions, we don't go through any carbocations, which means if something was cis to start, it's going to be cis in the products. Right? So you notice how the bromines are trans, right? Kind of like opposite sides. And the carboxylic acids are both hatched because they're on the same side, and the H's are on the same side. Now if we go look at the answers, you got to find that answer that matches that up. And so be careful that you don't, the easiest way to trick people is to, these will be trans, but then you mess around with the starting stereochemistry of the alkene, right? This matters. So these are on the same side. They should be the same wedged or hatched before. So for this one, there's a couple possibilities. We have a reactive nucleophile base. So that immediately makes us think about SN2 or E2. If it was going to be SN2, right, we of course would have inversion of stereochemistry, which means this would be the product. So this would be the SN2 product. But we don't see that product. So then that's not what's happening here. So it must be an E2 reaction. Now the other part of this is remembering what an E2 mechanism is. For an E2 reaction, you need to have things, the leaving group and the hydrogen, be anti-periplanar, be 180 degrees apart. Right? 180 degrees apart. When you see this, you recognize perhaps that's only possible with one type of alpha hydrogen. All right? So you can't, right, even though we want to obey Zaitsev's rule, which of course means we want to have the more substituted alkene, we can't overcome Zaitsev's rule, right, because we need to have things be anti-periplanar. This H and this bromine are on the same side of the ring. So they're not 180 degrees apart. They're looking right at each other. Right? They're looking right at each other. So you're going to have to take an H from this alpha position, either one of these, the one that's on the opposite side, right? So where one's hatched, that's going to allow for this elimination, this E2 elimination to take place, and that's how you get this as the product. All right, so a couple things are taken into account here. Do you understand SN1 or SN2 and E2, like when that happens, right? It happens with the reactive base or nucleophile. So you see an O minus, it can't be SN1 or E1, right? So then you're like, okay, SN2 or E2. If it was SN2, right, the first thing you remember about SN2, it needs to do with inversion of stereochemistry. So if this isn't a possible answer, then it has to be E2. What do you know about E2? E2, you need to have things be anti-periplanar, 180 degrees apart. The hydrogen leaving group need to be opposite sides. Now you always want to do Zaitsev's rule, right? More substituted alkene, but in this case, it's not. You want to put the pi bond there, but it's not possible because this H and this bromine are not 180 degrees apart. They're on the same side. So you got to go to this hydrogen over here, and so you make the less substituted alkene, but that's because you had to follow the anti-periplanar E2 rules. Okay, which most correctly represents the electron reorganization in the rate determining or slow step in the acid catalyzed E1 dehydration of this alcohol? Couple words to make sure. You heard E1. What do you know about E1s? How many steps is an E1 reaction? It is 2 steps. Right? The first step, you form a carbocation, and the second step is an elimination. 2 steps, right? Sorry, E1. Yeah, E1 is 2 steps. They say acid catalyze. If you hear acid catalyze, what do you know the charge overall of the molecule will be? Well, it will have to be acid catalyzed, right? H plus, so it's going to have to be plus charged. And they say reorganization. That means, right, they're basically saying, is there going to be like you make a carbocation. Is it possible to do a rearrangement? And they also say rate determining step. So the rate determining step of an E1. So for a reaction to have a rate determining step, technically it has to have more than one step, right? And so if you remember what an E1 reaction is, that's what really helps here. Two things really help. Do you know what an E1 is? And that acid catalyzed should tip you off. Because if you hear acid catalyzed, you should immediately eliminate what? Right? That has a minus charge. Nope. And also, electrons going to an O minus? No. This one, there's no plus charge. Acid catalyzed. Where's the acid? Right? If you have acid catalyzed something, remember I told you this. If you have H+, what's the first thing you do? That reacts. That's the best electrophile we got. Literally no electrons. The most electron deficient thing we got. H+, as far as you're concerned. Right? So now you're stuck with these two things. Well, here's the difference. So, the acid catalyzed part got you to the plus charge. And now the question is, do you know what an E1 reaction is? Because one of these is an E1 and the other one's an E2. Right? This one, that's an E2 reaction. Right? That's forming a pi bond and having the leaving group leave in the same step. That's an E2 reaction. It says E1, so this is the right reaction. Right arrows being shown. So really, if you look at this is kind of just silly. That can be eliminated without knowing anything, just knowing about arrows moving. You never see electrons going to an O minus. Then you need to know a little bit more. Acid catalyzed gets you to these two. Knowing E1 gets you to this versus E2. All right, so for this one is really, you see this, H3O plus is like strong acid, that's H plus. So you're going to do a protonation. Oops, there we go. You're going to turn the alcohol into a good leaving group. The leaving group is going to leave. You're going to make a carbocation. So this is like an E1 reaction. An E1 reaction, there's no good nucleophiles, so not SN1. So in acidic conditions, E1. And then in this case, because it's an E1 and it's carbocation, we're not worrying about things being antiperiplanar like we would in an E2 reaction. So this one, the most important thing to think about is Zaitsev's rule. Trying to make the most substituted alkene possible. So in that case, we're going to go this way. So there's your elimination, E1 style. And that's going to make the tri-substituted alkene versus eliminating the H up here would make a di-substituted alkene. So we want to go for the more substituted alkene in E1, Zaitsev's rule. In E2, we're worried about things being antiperiplanar, so we can't always go with the Zaitsev product, the more substituted alkene. So in E1, though, in this case, we can get the more substituted one. And that's the one we end up with. So one of the first reactions we learned, another addition reaction, is with alkenes and mercury acetate, step 1, and then sodium borohydride, step 2. This one parallels the the borohydride, the BH3 one, right? Hopefully you remember from this one, this is one of the first ways we learned how to turn an alkene into an alcohol. Now you see I've numbered the two carbons of the pi bond, carbon 1 and carbon 2. Carbon 2 is more substituted. So this is that Markovnikov, anti-Markovnikov thinking. So the mercury always gives us the alcohol in a Markovnikov fashion. So it gives us the Markovnikov product. Now, you don't need to know, right? I think sometimes we get bogged down in trying to know all the mechanisms. You don't need to necessarily know the mechanism here. What you do need to know for sure is when you see mercury, you think the OH, whether it's an alkene or an alkyne, the OH goes on the more substituted carbon. Right? The oxygen ends up on the more substituted carbon. Right? So that gives you an alcohol with alkenes. With alkynes, it gives you a ketone. Right? It's a little different if it gives you a ketone because there's that merization that has to take place. Still with me. Right? So the key here is, you kind of got to know the reagent. I mean, there's no magic here. Sometimes you got to know stuff. You see mercury, you think Markovnikov, oxygen, the more substituted carbon. Whether that's an alkene or an alkyne. That's the key to take home here. And it only adds one. It only adds one. So in this one, you're presented with these four different types of molecules, and you're given a carbon-13 NMR, and you're given a IR. So carbon-13, as you may or may not remember, or maybe didn't do a lot with, it's okay. Carbon-13 just tells us the numbers of different types of chemically non-equivalent carbons. So just like a proton NMR shows different H's have a peak, and a carbon NMR, different carbons have a peak. Now, there's no splitting, there's no coupling constant, so that's kind of nice. But for every peak in a carbon NMR, that means there's a different type of carbon in that molecule. So you can maybe look at these and figure out right away that these top two only have 3 types of carbons. Right? They have 1, 2, and then these 2 methyls are the same. 1, 2, 3, because these have the same chemical environment. They're the same distance away from everything. Right? They're essentially the same. They have the same type of hydrogens, so the carbons will be the same too. 1, 2, and 3. And so in the problem, we're showing a carbon-13 NMR with 4 peaks. So we know that the molecule has to have 4 different types of carbons. So we can eliminate these 2. Now these other 2 each have 1, 2, 3, 4, 1, 2, 3, 4, 4 different types of carbons. So the only difference now then is between the NH2 and the OH. So now we look at the IR. And if there's one thing you remember from IR, hopefully, you remember the OH peak is that big, broad, kind of drawn out thing above 3,000, right? It's a really big peak. And if you look at the problem, you don't see that. You don't see that. You see something that looks a little bit more subdued and like this kind of like fangs. And that's indicative of the NH2 group, the primary amine. So that is the one you want here, right? So if it was an OH, you'd see that big, broad peak, but you don't see that. Carbon NMR tells us 4 different types. That's the biggest takeaway there. The imidazole ring system, which contains 2 nitrogens, is found in the amino acid histidine. Great. Which statement is true regarding the basicity of the 2 nitrogens? So what do you need to think about here? We've had a question like this. You've had a question like this before. When they talk about basicity of the nitrogens, they're talking about the availability of those lone pairs, right, that I've drawn in, nitrogen 1 and 2. And what you got to think about, right, for basicity, some of the same factors we think about for acidity. How available is that lone pair? Is that lone pair doing resonance? If that lone pair is doing resonance, is it going to be very reactive? No, it won't be able to be very, very reactive. So if it's in a p orbital, it won't be very reactive because maybe it's doing resonance with something else. If it's in an sp2 orbital, right, that would make it more available. If it's in an sp3 orbital, even better, because sp3 is even farther away from the nucleus, right? So that lone pair would be even more reactive. So in this case, if you look at this nitrogen is sp2 hybridized. This nitrogen is also sp2 hybridized. How do I know it's sp2 hybridized? It doesn't have any pi bonds. But I see that this nitrogen is next to a pi bond here and next to a pi bond here. Meaning this nitrogen will choose to be sp2 hybridized. So it has a p orbital that it can put that lone pair in, because now that lone pair can do resonance. And you have to have a lone pair in a p orbital for it to do resonance, right? P orbitals need to line up, right? So this lone pair is actually going to be in a p orbital. It's actually part of an aromatic system, right? If you look at that, it's in a ring, planar. There's 3 pairs of lone pairs. That's an aromatic system, so it's really not available. This lone pair is in an sp2 hybrid orbital. Right? Is it doing resonance? No, it's actually perpendicular. Right? It's 90 degrees away from the p orbital system. So this nitrogen this lone pair would be much more basic, much more reactive. So then you look at the answers, right? Both are strongly basic. Nitrogen 1 is more basic, nitrogen 2 is more basic. Neither would be considered more basic. So the right answer here is nitrogen 1 would be considered much more basic, right? Because its lone pair is not doing resonance, right? Now, if you had another example, take it a step further, right? But you could say that this nitrogen's lone pair is more reactive because this is sp3 hybridized, and that lone pair is in an sp3 orbital, which is farther from the positively charged nucleus. So that lone pair is being held less tightly, right? So hybridization and resonance playing a role here in the basicity, how reactive of nitrogen is, how reactive its lone pair